You are sitting outside on a clear afternoon. The sky is blue, the air is warm, birds are singing. Then, in an instant, the sun is gone. Not dimmed, not fading, gone. Completely and instantaneously removed from existence. What happens next is not what most people think. The sky does not go dark immediately. The earth does not instantly freeze. You would not even know for 8 full minutes. And in the hours, days, and weeks that follow, the sequence of events that would unfold is so precisely choreographed by the laws of physics that scientists can describe it almost minute by minute. This is not a story about disaster. It is a story about how deeply, completely, and invisibly the sun controls every single aspect of life on Earth. And understanding what would happen if it vanished is one of the clearest windows into what it actually does while it is still here. Welcome to Space Review. We ask the questions that sound impossible and follow the science wherever it leads. Subscribe and hit the bell so you never miss an episode, because what we are about to walk through will change how you think about the star at the center of our solar system permanently. The sun is so constant, so reliable, so woven into the fabric of every day of human existence that it is almost impossible to think of it as something that could simply not be there. It has risen every morning for 4.6 billion years. Every ecosystem on Earth is built around its energy. Every weather system, every ocean current, every molecule of food you have ever eaten traces its energy back to sunlight. The sun is not just a light source. It is the engine of an entire planetary system, and Earth is a passenger, entirely dependent on that engine continuing to run. So what happens when it stops? The answer unfolds across multiple timescales, from the first 8 minutes to the first hour, from the first day to the first year, and eventually to a final state that is as alien as anything in the known universe. Each phase reveals something profound about the hidden architecture of the world we live in, and some of what you are about to hear will be genuinely surprising. Before the disappearance, it is worth being precise about what exactly would be lost, because most people dramatically underestimate the sun's role. The obvious one is light. The sun illuminates the earth, drives photosynthesis, and makes plant life possible, which in turn makes almost all animal life possible. Remove the light, and you remove the base of nearly every food chain on the planet. But light is only the beginning. The sun's heat drives the entire atmospheric circulation of Earth. Temperature differences between the equator and the poles, between land and ocean, between day and night, all of these create the pressure gradients that generate wind. Wind drives ocean surface currents. Ocean currents distribute heat around the planet, keeping regions far from the equator habitable that would otherwise be frozen. Remove the sun's heat, and the entire atmospheric and oceanic circulation system begins to shut down in ways that cascade through every climate system on Earth. The sun also provides the gravitational anchor that holds the entire solar system together. Every planet, every moon, every asteroid, every comet in our solar system orbits the sun. Gravity travels at the speed of light, a fact confirmed by Einstein's general relativity and supported by gravitational wave observations. Remove the sun's mass, and its gravitational influence does not disappear instantly. It disappears at the speed of light, propagating outward as a wave of released gravitational binding. Earth would feel it at exactly the same moment it sees the sun go dark, 8 minutes after disappearance. And then there is the solar wind. The sun constantly exhales a stream of charged particles that fills the entire solar system and maintains the heliosphere, the magnetic bubble that shields the inner planets from the most energetic cosmic rays streaming in from the galaxy. Without the solar wind, the heliosphere begins to collapse, and Earth's radiation environment starts to change in ways that matter over longer timescales. The sun disappears. On Earth, nothing happens. Not yet. Light from the sun takes approximately 8 minutes and 20 seconds to reach Earth. That is how far away the Sun is, 150 million kilometers, expressed in the one universal constant that never changes, the speed of light. For those 8 minutes and 20 seconds after the Sun ceases to exist, Earth continues to receive the last photons the Sun ever emitted. The sky stays blue. The temperature holds. Birds keep singing. Your shadow is still there. Somewhere around the world, people are taking photographs of the sunshine without knowing they are photographing light from a star that no longer exists. Then, 8 minutes and 20 seconds after disappearance, two things happen simultaneously. The last light reaches Earth, and the last gravitational influence reaches Earth. The sky goes dark, and Earth, no longer bound to the Sun's gravity, stops orbiting and begins moving in a straight line, following the trajectory it was on, at the exact moment the Sun vanished. This is Newton's first law. An object in motion continues in a straight line unless acted upon by a force. The force is gone. So Earth travels in a straight line into space at roughly 30 kilometers per second, its orbital velocity at the moment of release. Immediately, every other planet does the same thing. Mercury, Venus, Mars, Jupiter, Saturn, Uranus, Neptune. Each one released from its orbit at the speed of light, propagates outward from where the Sun was. The solar system, in the space of a few hours, disassembles itself. The planets scatter into the galaxy on their own independent trajectories, some toward the galactic center, some outward, none of them anywhere near each other. In astronomical terms, the solar system ceases to exist almost instantly. Back on Earth, the immediate aftermath of the darkness is not cold. Not yet. The atmosphere holds an enormous amount of heat, and it does not release it instantly. The first hour after the Sun disappears would feel, to anyone outside, roughly like a normal night. Temperatures begin to drop, but slowly. People in regions where it was daytime would experience a sudden transition to something resembling dusk, and then complete darkness. The moon, which reflects sunlight, would also go dark. The only light in the sky would be starlight, and the stars themselves, so long washed out by the sun's glare, would appear in their billions for the first time to billions of people who had never truly seen a dark sky. Panic would begin, obviously. Power systems, designed to handle demand spikes on hot days and cold nights, would face demands outside any modeled scenario as heating systems everywhere switch on simultaneously. Communication networks would face extraordinary loads. Governments would face decisions with no precedent and no playbook. But physically, in terms of temperature and atmosphere, the first hour is survivable almost anywhere on Earth. The crisis is coming. It is just not here yet. Temperature is where the real catastrophe begins to build. Without solar input, Earth starts losing heat to space through a process called radiative cooling. The rate of cooling is not uniform. The atmosphere, oceans, and land all release heat at different rates. The atmosphere cools faster than the oceans because it has less thermal mass. The oceans, which store an enormous amount of heat, cool more slowly and actually become the primary source of warmth for coastal regions for the first days and weeks. Within the first week, average global surface temperatures would drop by several degrees. This would be catastrophic for agriculture and ecosystems, but not immediately lethal in most inhabited regions. The real concern is what happens in the weeks that follow. Photosynthesis stops immediately when sunlight disappears. Within days, plants begin to die. The food chain, which depends almost entirely on living plants at its base, begins to collapse from the bottom up. Agricultural crops would fail within days to weeks, depending on the species. Forests would survive longer on stored energy, but would eventually succumb to cold and darkness. The ecosystems built over hundreds of millions of years of solar-powered evolution would begin an irreversible unraveling. Within a year of the sun's disappearance, Earth's surface would be almost unrecognizably hostile. Average surface temperatures would drop to approximately -100 degrees Celsius within a year, according to most scientific estimates. At those temperatures, the atmosphere itself begins to change. Carbon dioxide, which makes up a small fraction of Earth's air, freezes at around -78 degrees Celsius. Within months of the sun's disappearance, carbon dioxide would begin snowing out of the atmosphere and collecting on the surface as dry ice. Nitrogen freezes at -196 degrees Celsius, and over longer timescales, even the nitrogen that makes up most of Earth's atmosphere would eventually freeze, leaving the planet with almost no atmosphere at all, more closely resembling the surface of Pluto than the world we know today. The oceans, however, would not freeze entirely. Not quickly. Water has an extraordinary heat capacity, and the deep ocean in particular would hold its warmth for an extended period. More importantly, liquid water could persist beneath a growing layer of surface ice for potentially billions of years, kept warm by the heat of Earth's own geothermal activity, the residual heat from planetary formation, and the ongoing decay of radioactive elements in the mantle and core. Scientists estimate that the geothermal heat flux at the ocean floor, roughly 0.1 watts per square meter, is enough to maintain liquid water at the very bottom of the ocean, even in the complete absence of sunlight. And here is where the story takes its most unexpected turn. The most surprising thing about a sunless Earth is not what would die, it is what might survive. On Earth today, there are entire ecosystems that do not depend on sunlight at all. Deep ocean hydrothermal vent communities, living in complete darkness at crushing pressures, powered entirely by chemical energy from the vents, are among the most productive ecosystems on the planet by biomass. These communities include tube worms, crabs, shrimp, fish, and vast microbial mats that use chemosynthesis rather than photosynthesis as their energy source. Every one of these organisms would continue to function after the sun disappeared, completely unaffected by the darkness above. Even more remarkably, scientists have discovered microorganisms living kilometers deep in Earth's crust, feeding on hydrogen produced by chemical reactions between water and rock, in an environment that has been essentially isolated from the surface for millions of years. These deep subsurface microbes have no connection to the sun whatsoever. They are powered by the planet's own internal chemistry. After the sun vanished, they would never know anything had changed. The deep ocean, kept liquid by geothermal heat, protected from the frozen surface above by kilometers of water and ice, could remain a viable habitat for simple life, essentially indefinitely. If any multicellular life could adapt to those conditions over evolutionary timescales, life on Earth could continue in the sunless deep ocean for as long as Earth's core remains hot. That is potentially billions of years. Life on Earth, it turns out, is more deeply rooted than the sun. The scenario of a sunless Earth, while hypothetical in its most extreme form, has direct relevance to one of the most active areas of current astrobiology research. The discovery that life can exist in complete darkness, powered by chemical and geothermal energy alone, has dramatically expanded the range of environments where scientists believe life might persist elsewhere in the solar system. Europa's subsurface ocean, kept liquid by tidal heating from Jupiter's gravity rather than sunlight, is now considered one of the most promising places in the solar system to search for life. It is, in many ways, a naturally occurring version of a sunless Earth ocean. The same logic applies to Enceladus, to Titan's subsurface ocean, and to dozens of other icy moons orbiting the giant planets. All of them receive almost no sunlight at their surfaces. All of them may have liquid water below, powered by internal heat rather than solar energy. If life can survive on a sunless Earth in the deep ocean, the case for life in these sunless subsurface oceans becomes substantially stronger. The James Webb Space Telescope is currently studying the atmospheres of distant exoplanets, some of which orbit stars so dim and cool that they receive very little energy compared to Earth. Understanding whether life can persist in low-light environments, using the logic of geothermal and chemical energy rather than photosynthesis, is central to interpreting what Webb finds in those atmospheres. The thought experiment of removing the sun reveals something that is easy to forget in the comfortable, sunlit world we inhabit. The conditions for life are not as fragile as they appear from the surface, but they are also not as robust as our experience of abundant sunlight might suggest. For humanity specifically, the disappearance of the sun would mean the end of civilization as we know it within weeks, and the end of surface life within years. There is no technology currently available, and none plausibly developable on short timescales, that could replace the energy input of the sun for 8 billion people. The only survivors would be those who could reach deep underground or deep underwater environments, and even then, survival would depend on access to geothermal heat and the chemical energy of the deep Earth, rather than anything that currently sustains human civilization. This makes the sun not just astronomically important, but existentially important, in a way that most people never consciously register. It is the single most critical factor in the continued existence of complex life on this planet, and it is something we take so completely for granted that we rarely think about it at all. The good news, and it is very good news, is that the sun is not going anywhere. It is approximately halfway through its roughly 10 billion year lifespan. It will continue burning stably for another 5 billion years before it begins expanding into a red giant. The disappearance scenario is physically impossible under any natural process. The sun cannot simply vanish. But thinking through what would happen if it did is one of the most illuminating exercises in understanding what it does while it is here. If the sun disappeared right now, you would have 8 minutes and 20 seconds that felt completely normal. Then darkness, then cold that builds slowly, relentlessly, and without mercy across weeks and months. Then a frozen surface under a collapsing atmosphere, with an ocean slowly sealing itself under thickening ice, while the deep water below stays liquid, warmed by the planet's own ancient heat, hosting communities of life that never needed the sun to begin with. The solar system would scatter. The planets would drift into the galaxy as independent wanderers, cold and dark and silent. Earth would become a rogue planet, carrying its hidden ocean and its deep rock microbes into the interstellar void, surviving in the dark for billions of years. What the sun's disappearance reveals is the true shape of dependency. Almost everything visible, almost everything complex, almost everything that makes Earth recognizable as the world we know, is built on 8 minutes of light from a star 150 million kilometers away. Take away those 8 minutes, and the surface of the world unravels with stunning speed. But life, stripped down to its most fundamental form, turns out to be more durable than the star itself. The sun gives us everything we call civilization, but the deep Earth gives life something even the sun cannot provide: permanence. If this changed the way you look at the sky tomorrow morning, share it with someone who has never thought about what the sun actually does for us every single day. Drop a comment below, telling us what you think the most surprising part of this scenario was. Was it the 8-minute delay? The ocean surviving for billions of years? The deep rock life that would never notice? Subscribe to Space Review, because next time we are taking on another question that sounds simple and turns out to go somewhere extraordinary. We will see you there.